much simpler, I think, than rationals. But let's talk about what this word means. All right, we're going to use some practical examples and then talk about the math behind an exponential function. So let's go ahead and look at the math. Make sure you take good notes today, because we'll be on this unit for a little while. When you have a variable in the exponent, something we really haven't looked at, remember we looked at polynomials, the variables in the base, the exponent is a number. So when the exponent is a variable, that's when you have an exponential function. So for this particular example, when we strip it down to its basic form, we have f of x equals a. So a could be a number, 2, 3, 4, 5, 6. Okay? It does need to be a whole number for it to be an exponential function. If it's a negative number, it gets really weird. We're not going to look at negative bases, just positive bases. And then the exponent is a variable. Okay? So an example, like I said, would be 2 to the x. That's an exponential function. Or 3 to the x. Those are the two most common. So notice, a has to be positive. And also, if a were 1, it wouldn't really be an exponential function. Does anybody know why that is? Like if I just wrote, let's do a different page here. Right, 1 to the x is always 1. 1 cubed, 1 to the 4th, 1 to the negative 7th. It's a straight line. So it's not really an exponential function. But as long as the base is positive other than 1, you have an exponential function. Any questions on that? Okay, so let's make some more notes here. An exponential function grows really fast as time goes on. Okay? Grows really fast as time goes on. Grows faster than a polynomial, grows faster usually than a rational. I'm going to try to pull up my little car app here and demonstrate that for you guys so you can kind of see how it works. But yeah, it goes really fast as time goes on. When it first starts out, it doesn't go very fast. So I'll get my car app going and we can take a look at that, do a little car race with some functions. So bacteria growth. And so this is why the flu bug sometimes becomes so prevalent for certain seasons. Because when the bacteria first starts out, or virus or whatever, it doubles or triples or whatever, depending on the rate at which it's growing. And so sometimes with a virus or bacteria, you can see that it starts out kind of slow and then it jumps. So that's an example of exponential growth. You can also have exponential decay, by the way. Will be money, specifically interest accounts. And as you can see, the higher the interest rate, the more money you're going to get over time. So this is still not working. Okay, so an interest account is another example.
What would it be?
Compound interest is a lot different than simple interest. So compound would be an example of. Ladies, I need you to pay attention, or I'm going to move you. I've been asking a lot of times over the past couple of days. You're not being respectful. Population growth. Okay, we know that the human population is getting bigger, and this is an actual graph of human population over time, going back to 1750, so colonial days. Look how steady the growth was for a while, and then it kind of shot up after 1950. That's what happens with an exponential graph. It's kind of flat for a while, not exactly flat, and then it goes up. And so this is projected unto 2050. They think it's going to be about 10 billion people. That's exponential growth. Exponential growth doesn't just shoot up all at once. It's gradual, and then it kind of shoots up. So we'll take a look at some simple exponential functions. Here's some examples. Go ahead and write these down. The first two are exponential because what? There's a variable in the exponent. This one is not exponential because the base, the third one, my screen cut out again. The third one, the base is is a variable. The exponent is a number. It doesn't work. That's a polynomial. Okay. You're going to see something like this on your worksheet. These are different numbers, and you'll have to. No, I can just walk you through on the worksheet. But on your worksheet, you'll plug in these same numbers: -2, -1, 0, 1, 2. I don't know if it has a slot for 3. It doesn't really need one. Anyway, when you have a negative exponent, thank you, you can make it positive and put it under 1. So for example, 2 to the -2 is 1 over 2 squared, which is 1/4. You can also plug that into your calculator. Okay, I can go here and plug in 2 to the -2, and it's going to give me 0.25, which is the same as 1/4. But that's how you evaluate it by hand. So like on your worksheet, you'll have 4 to the -3 for the first one. That's just 1 over 4 cubed. That'd be 1 over 64, which is a really tiny number. It almost touches the x-axis. So what you'll do is you'll find all these y values and then plot them on a graph, right? So each of these rows represents a point. Let's look at f of x. F of x equals 2 to the x. If you were to plot all those points, it would be this blue line right here. Okay, so that's our 2 to the x. And if you plot all the points for g of x, you get this red line. Now here's what's interesting. You notice g of x has the bigger base of 3. It ends up being smaller before you get to 0. Okay? And that's because you have a negative exponent here. It's going to make the number smaller because you're dividing by a bigger number. When it gets to 0, they're the same because anything to the 0 power is 1, so they cross. And then once it gets past 0, the red function g, which has a bigger base, ends up being bigger. Why? Because, for example, 3 to the first is 3, 2 to the first is 2, so obviously it's bigger. And you can see it takes off more as time goes on because it has a bigger base. That's probably the most important thing to know from this lesson. The bigger the base, the faster it's going to grow past 0, but in fact before 0 it's going to be smaller. At 0 they cross. So here's a couple things to note about that. First of all, the range for an exponential, you need to write that down somewhere. It might even be on your worksheet. I think that's one of the questions. The range for exponential functions is anything bigger than 0, not including 0. Okay? Okay? It will never touch 0. It will get closer and closer. But you can't take a number and raise it to an exponent and get 0 back. It's always going to give you something back, even if it's really small. So that's why the range is anything from anything past 0 up into infinity. So you could just say all positive numbers for the range. To the domain, the answer will also be the same. Domain is all real numbers. Okay, you can plug in anything into the exponent and get something back. You won't get an undefined back. It's not like a rational function where you can't plug in 0 to the bottom. If it's 1 over x, you can't plug in 0 because you get undefined. With an exponential function, you can plug in anything. You can see this on the graph. Okay, if I run a vertical line across this graph, it's always going to touch at least once. So domain, all real numbers. Range, like we already talked about, it will not cross the x-axis. If the range is anything past 0, then it'll never touch the x-axis. And again, that's anything in the form a to the x. There's ways to change it and make it move down, but we're not going to talk about that right now. It's always going to cross the y-axis at 1, 0, 1. Okay, so if a is a number bigger than 1, so if the base is bigger than 1, so in these examples 2 and 3 are bigger than 1, it will always increase. Okay? You can see that on these graphs. They're always going up. We won't spend as much time on fractions, but if the base is a fraction, see if I can go down here and show you an example. So for example, if you had 1/2 to the x power, your a would be between 0 and 1. In fact, that graph will decrease. Again, we won't spend a lot of time on that, but it'll actually look like that. It'll go the opposite way. Yeah, let me pull up an example of that actually. We can take a look at that. Let's change this to 1/2 to the x power. Okay? So you can see it does the opposite. That's for any fraction. That's a base. All right. Let's see.
Decreasing, is it, what's the, like,
Yeah. Increases as long as the base is a whole number. Or a number bigger than 1, rather.
Okay.
Decreases if it's a fraction, a proper fraction, meaning between 0 and 1. It does have a horizontal asymptote at y equals 0. You can see that on the graph. At the beginning, it curves around y equals 0, but doesn't touch. So an exponential function doesn't have a vertical asymptote. It doesn't have a slant, but it has a horizontal at y equals 0. Inverse I'm just going to mention right now. We're going to talk about logs after we go through exponentials. The inverse of an exponential is a log. Okay, so I don't expect you to know anything about logs right now, other than the fact that the log is the inverse. We can't really talk about why until we learn about logs. Okay, so let's answer a few questions about this. You can kind of look at your worksheet to get an idea. I don't expect you to write any of this down. Ah, it went away again. We'll just have to talk about it. Oh, it didn't show up. All right, which function? The x. Yeah, 3 to the x will grow faster than 2 to the x. And that's because why? Has a bigger base. Right. Going back to compound interest. Okay, so 3 to the x will grow faster because it has a bigger base. Next question. Let's see. Oh, this is an example. If you had 100 to the x, look how big your y value would be at 2. It'd be 10,000. You know, so that one would like shoot up like that real quick, and that's because it have a really big base. Which function values are bigger? So again, the y values are going to be bigger for the smaller base when x is less than 0. Going back to the graph, you can see that.
want to write that down?
No. 2 is smaller, but if you look down here at the graph, it's bigger for negative values. At 0, they're the same, and when it's greater than 0, the red function, which is 3 to the x, becomes bigger. So that's all this slide means right here. They're always going to be equal to 1 at 0, and then the bigger function with the bigger base will be bigger for positive values. That's just a generalization. So when a is less than b, when a is smaller, that's what's going to happen. Whenever it's negative, the smaller base will be bigger. They'll be the same at x equals 0, and then whenever x is bigger than 0, the bigger base will be higher than the smaller base. So let's see if we can pull up that car race. All right, so I did some modifications to make it a closer race, but if you notice the red car, there's an x in the, there's a variable in the exponent. The green car is a square root function. The blue car is a polynomial. The yellow car is a trig function, which we'll study later. So let's see which one wins. Remember, an exponential function is slow to start out, and then it takes off. So let's take a look.
Blue. Oh,
Ah.
red.
So the red won. So an exponential function will eventually take off, and it'll grow faster than the other functions. So that's pretty much what I'm going to show you. The blue function is polynomial.